morning, gentlemen. In my previous session, I had mentioned about theoretical sunrise and sunset with the theory part of it. And also I had briefly explained to you about the rising and setting of celestial body for an observer on the Earth's surface. Gentlemen, the fundamentals to be very clear. Earth is rotating from west to east. Because of that, all celestial body, including the sun, appears to rise in the east and set in the west. The entire theory has been already explained to you. Now we have to make use of this for our navigation purpose. So if I have to tell you exactly for two purposes for which we are making use of it, it is to correct the ship magnetic compass, that is, to find out the deviation of the compass, we make theoretical sunrise or sunset. How? We measure the bearing of the sun from the ship and then calculate the deviation for that heading. Now let us look at what is the second purpose. Second purpose is our gyro, which is fitted on board a ship, may have crept in with some error. It is the responsibility of the officer of the watch at the bridge to ascertain the gyro is without error. If he has to know if the gyro is having error or not having error, it can be easily found out by using the theoretical sunrise and sunset bearing. So it is our responsibility as a mariner, while doing watch at the bridge, to take bearing of the sun exactly when it rises and exactly when it sets. What does it mean? It is when the sun is above the rational horizon, just crossing the rational horizon, it is rising or setting. So let us look at it with explanation more on the mathematics involved in the spherical triangle. As I mentioned a few seconds back, theoretical sunrise and sunset occurs when the true sun center is on the observer's rational horizon. Altitude of true sun is 0. And because of that, from zenith, that is the observer's position at the celestial sphere, from there to the rational horizon, which is 90 degree already. So zenith distance is also 90 degree. P is a triangle, spherical triangle, with one side zx 90 degree can be used. I will explain that. Now we need to look at the Napier rule. Napier rule pertaining to spherical triangle. So let us, before going to the Napier rule, let us look at what are the types of spherical triangle. Just a recapture of your memory. There are 3 types of spherical triangle. One is oblique spherical triangle, another one is right angle spherical triangle, third one is quadrangle size spherical triangle. What is oblique spherical triangle? It is the normal spherical triangle where all 3 sides and also all 3 included angles are not equal to 90 degree. So all 6 angles are not equal to 90 degree, then that spherical triangle is called oblique spherical triangle. What is right angle spherical triangle? Here, the included angle between 2 sides, if any one of them is 90 degree, then it is termed as right angle spherical triangle. Whereas other 5 angles, that is 3 sides and 2 other included angles, will not be 90 degree. Only one. If it is 1, then it is called right angle spherical triangle. Now let us look at what is quadrangle size spherical triangle. It is different from right angle spherical triangle. Here, the sides between position A to position B or between 2 positions, the side is equal to 90 degree and the included angles are not 90 degree. One of the sides is equal to 90 degree, then that spherical triangle is termed as quadrangle size spherical triangle. When one side, what I told you, is equal to 90 degree, here the zenith distance is equal to 90 degree at theoretical sunrise, which we have seen some time back, because the true sun is at the rational horizon. When it is at the rational horizon, true altitude of the sun is 0. Because of that, from the zenith to the rational horizon, which is 90 degree, equal to zenith distance and 90 degree. Here we need to understand the proof of the equation, which we are going to use it for finding general error and also the magnetic compass deviation. Sine amplitude equal to sine declination into secant latitude. This is the formula should have been understood. This is the formula we apply when theoretical sunrise occurs for those two purposes which I mentioned a few minutes ago. Gentlemen, let us look at the theoretical sunrise and again the rational horizon diagram. Assume this is the rational horizon and you have an observer who is in the northern hemisphere. The prime vertical, principal vertical, and this is the northern direction, this is the southern direction, east, west. Assume that observer is in the northern hemisphere. Because of that, equinoctial would be south of him. That is, Q is south of him, south of Z. Zenith is Z. Now, the elevated pole P would be closer to Zenith. The distance which I explained in the previous session between Q to P is 90 degree, Z to N is also 90 degree. So N to P is nothing but equal to Z to Q, that is the latitude of the observer. As the latitude increases, the elevated pole comes closer to zero. This is one aspect. Now what we are talking about in theoretical sunrise. When theoretical sunrise occurs, as it is mentioned earlier, the sun is at the rational horizon. So let us assume sun is at the rational horizon. Also it is having northerly declination for this explanation. If the sun is at the rational horizon, altitude of the sun at this time is 0. So from zenith, the distance to the sun is called zenith distance, Zx. This zenith distance is equal to 90 degrees. And from P to X, if you draw, this would be the part of that. That is from Q to X is the declination, P to X is polar distance. That is 90 degree minus declination. And we know Z to P, what I have termed earlier, Z to Q is the latitude. So this angle between P to Z is called co-latitude. So here we have a unique condition where this particular spherical triangle has got 3 sides and 3 included angles, and out of that 6 angles, 3 included angles are not equal to 90 degrees. Other 2 sides, that is polar and polar distance, are less than 90 degrees. Whereas zenith distance between Z to X, when the altitude of sun is 0, at theoretical sunrise is 90 degrees. So since we have one side is equal to 90 degrees, we have to use the Napier rule, which is applicable for quadrantal side spherical triangle. So what happens? The Napier rule. Let us look at it. You draw a 5-part circle. You take out Zx, which is 90 degree outside. Out of the 6 angles, 1 angle has been taken out. Thereafter, moving clockwise on the spherical triangle, name all other angles. First angle after this is Z. Next one, it is PZ. PZ, we got to name it 90 minus PZ. Next one, it is angle P. Here we need to name it P minus 90. Why P minus 90? It is the Napier rule for quadrantal side spherical triangle. You would have seen earlier for right angle side spherical triangle, it would be written 90 minus P. Next is, it is Px, where we write it 90 minus Px. Next angle is x. Gentlemen, what are the things we know? Values which we know, we put a tick. We know the PZ because latitude of observer is already known. We know that declination of the sun for that day, so we can put a tick here also. What we need to find out, what is our purpose? To find the zero error. That means to get the sun's bearing. How the sun bearing can be observed from us? If we know this angle, I can find out sun bearing. So we need to find out what is Z. That is nothing but azimuth. This azimuth, if we can find out by using the Napier principle, Napier rule, it will be fine. Now we are concentrating the equation sine amplitude equal to sine declination into secant latitude. Now, as per Napier rule, we got to understand sine middle part is equal to cos of opposite part. That is multiplication of both opposite parts. Let me write it. If I take these three angles which we are playing around, this if I consider the 90 minus px as the middle part, for other two are opposite part, that is z and 90 minus pz. So let us apply that rule. Sine 90 minus px equal to cos of z into cos of 90 minus pz. So multiplication of cos value of two angles which are opposite would be equivalent to sine of the angle which is 90 minus px. Now if I expand it, this becomes cos px, this can be written as cos 90 minus amplitude into sine pz. Now what does this amplitude have come? Amplitude is nothing but the angle between prime meridian and the vertical circle passing through the heavenly body, in this case sun. So Zx and Ze, this angle is called amplitude, which is nothing but 90 degree minus azimuth. So since amplitude is 90 degree minus azimuth, I have put cos Z as cos 90 minus amplitude. Now if I go for further expansion, Px can be written as cos 90 minus declination equal to sine amplitude, because sine cos 90 minus amplitude equal to sine amplitude. Then it can be sine Pz can be written as 90 minus latitude. Once again, apply the same principle. 90 minus degree would be, when the cos is there, it will become sine. So it becomes sine declination in this case. Here it will remain sine amplitude, and here it will become cos latitude. I need to take out sine amplitude to one side. If it is the case, sine amplitude equal to sine declination divided by cos lat, which is equal to sine declination into secant lat. The proof of the equation is already obtained. This is what we need to understand. So, when we want to find out what is the actual sun bearing at sunrise, theoretical sunrise, or in the case at theoretical sunset, the sun would be at the rational horizon, altitude will be 0. The zenith distance would be 90 degrees. Then it becomes a spherical triangle, a special one, which is the quadrangle spherical triangle. By applying the Napier rule, as I have explained to you, we can find out the angle of amplitude or azimuth. The amplitude, once you find out amplitude, whether east of, north of east or south of east, as I explained earlier, this is required to know. So we know the true bearing of the sun at theoretical sunrise. By knowing the true bearing of the sun, now you take with the gyro compass the bearing of the sun. If it is different, then there is a gyro error. If the observed bearing from the gyro compass is less than the true bearing, then gyro is reading low. If the observed bearing of the sun at sunrise is more than the calculated true bearing with this formula, then gyro is reading high. With that principle, that is the principle which is we use for finding the gyro error. Similarly, by knowing the true bearing and also compass bearing which you have got, we can, if the variation in the area is known to you, by applying CDMVT rule, that is CDMVT. V is variation, D is deviation, C is compass heading, and true heading, and magnetic heading. So, with this principle, we can find out either the deviation or the variation. If the variation is generally plotted on the chart, we can come to know for that area what is the variation. So, if I know the variation and I calculate the true bearing from this formula and also observe with the compass what is the bearing of the sun, then I can find out what is the magnetic heading, and difference between compass and magnetic heading will give you the deviation. I hope you have understood the use of theoretical sunrise and sunset for application of celestial navigation. Thank you.